Perhaps the best reason to study coordination compounds, especially those that contain transition metals, is that they're colored. For example, the mineral alumina is a colorless solid. In alumina, aluminum is surrounded by 6 oxygens. If aluminum is switched for chromium, then we get the gemstone ruby, which is red. So changing the metal changes the color of the substance. Dry-rite is a drying agent that uses a cobalt color indicator that tells you whether the substance is wet or dry. The ion cobalt tetrachloride is blue. Note that it has 2 waters and 4 chlorides bonded to the cobalt. If we substitute 4 waters for the 4 chlorides, then the compound turns pink. So changing the substance bond to the cobalt changes the color of the compound. Organic light-emitting diodes are used in TVs and use different colored compounds. Different metals and different substances bond to the metals gives different colored compounds. The days are getting longer and warmer, so it's grilling season. The color of the meat can tell you something, and that color depends on myoglobin. Myoglobin is a big protein found in muscle. The iron in myoglobin binds to oxygen or other substances. The substance that binds to iron determines the color of the myoglobin. You're looking for a nice steak to grill. Which one would you buy? The brown one doesn't look good. That's from water bound to the iron in myoglobin. The red one looks good. That's from oxygen bound to the iron in myoglobin. The purple-red one doesn't look so appealing. There is no oxygen bound to the iron in myoglobin. In myoglobin, there is a big nitrogen compound bonded to the iron. The color of the myoglobin depends on the charge on the iron as well as the 6th substance bonded to the iron. So when oxygen O2 is bonded to the iron, myoglobin is red. When water is bonded to the iron, myoglobin is brown. And when carbon monoxide is bonded to the iron, the myoglobin is red. You're at the store trying to decide which piece of meat to buy. You don't know that each piece of meat is 1 week old. You decide to buy the appealing red piece rather than the brown piece. The red piece of meat has been exposed to carbon monoxide, which binds to iron, which turns the myoglobin red. With the brown piece, water is bound to the iron, which makes myoglobin brown. So each 1 week old steak is really the same quality. So the next time you're shopping for steak, if the meat is red, it's oxygen bound to the iron in the myoglobin. If the meat is brown, it's water bound to the iron in myoglobin. And when you cook your steak, the proteins unfold and get denatured, and all these wonderful reactions like the Maillard reaction occur to turn your steak brown with all those delicious smells. Smoking meat will produce a pink smoke ring on the outer layers of the meat. The smoke ring is due to NO or NO2 bound to the iron in myoglobin. People love their bacon. I saw bacon ice cream once. Cured meats like bacon use curing salts such as potassium nitrate or sodium nitrite. The meat turns pink when NO binds to the iron in myoglobin. We learned earlier that a covalent bond forms when an unpaired electron from one atom combines with an unpaired electron from another atom to form a single covalent bond. The colored compounds we looked at earlier are examples of coordination compounds. Coordination compounds involve coordinate covalent bonds. A coordinate covalent bond forms when a lone pair from an atom called a ligand forms a bond to a metal. In each case, the bond consists of 2 electrons. The difference is the source of the electrons. Note also that the coordinate covalent bond is a polar covalent bond, but not so polar where it's an ionic bond. Organic compounds involve carbon and the octet rule. Coordination compounds involve transition metals and an expanded octet. Transition metals can have an expanded octet because d orbitals are involved. Organic compounds and coordination compounds both involve covalent bonds, but organic compounds are often white, whereas coordination compounds are often colored. Coordination compounds are colored because of the d orbitals and because of the atom called the ligand bonded to the metal. When you have a transition metal all by itself, d orbitals are all the same energy. When a transition metal bonds to 6 ligands in an octahedral shape, 2 of the d orbitals go higher in energy, 3 of the d orbitals go lower in energy. The increase or decrease in the energy of the d orbitals is due to the orientation in space of each d orbital. The energy difference between the d orbitals, also called the d orbital splitting, depends on the ligand bonded to the metal. That energy difference determines the color of the coordination compound. We looked at the cobalt color indicator in dry-rite earlier in this video. In cobalt tetrachloride, the ligands are water and chloride. In cobalt 2+ aqueous, the ligands are water only. Cobalt tetrachloride is blue. That means that compound absorbs orange, its complementary color. Remember the color wheel. Cobalt 2+ aqueous is pink. That means that compound absorbs green. Here is the cobalt d orbital splitting in cobalt tetrachloride. Stop the video and show the d orbital splitting in cobalt 2+ ion. And the answer is green is a higher energy than orange, therefore delta E for the d orbital splitting should be greater in cobalt 2+ aqueous than cobalt tetrachloride. Substituting 4 water ligands for the 4 chlorides splits the d orbitals more and changes the color. Many transition metals are found in the human body and exist as coordination compounds. Iron is the metal in hemoglobin which binds to oxygen. This is the heme part of hemoglobin. Note that nitrogen forms 4 coordinate covalent bonds to iron. And oxygen also forms a coordinate covalent bond to iron. This zinc coordination compound is used in dye-sensitized solar cells. A ligand is the source of that lone pair which forms a coordinate covalent bond. These ligands help deliver drugs to target cells. Citric acid is found in orange peels. The citric acid can bind to copper ion to remove copper from water. Now I know you remember your acid-base equilibrium principles, so stop the video and answer these 2 questions. The answer to question 1 is -2. For the second question, remember that this structure of citric acid is the fully protonated form at low pH. Raise the pH and the most acidic proton is lost first. At the first endpoint, the charge is going to be -1. Continue raising the pH and the second proton is lost. At the second endpoint, the charge will be -2. Now, don't you hate it when you're trying to pour salt out of its container and it's all caked together? This compound, yellow prussiate of soda, is used as an anti-caking agent. Although this compound contains cyanide, the iron-cyanide coordinate covalent bond is strong enough so the cyanide doesn't dissociate so you won't get poisoned.